Okay guys, first things first, we're going to talk about binary and then we're going to talk about basic digital chips. We're going to talk about gates. But first of all, we got to learn how to speak in basic binary. Now binary is actually really easy. It's just a matter of grasping how it's counted. Now it's counted from really kind of from the left to right, as opposed to from right to left, like a normal number. So as you can see, I'm gonna make the I'm gonna write down the binary equivalents to the decimal numbers on the right. So this number is the least significant bit, the LSB, whereas this one is the most significant bit, which is the MSB. So we're always counting from the left to right. If we had 1000, it would be actually much bigger than 1000 from left to right, or rather 0001. So if we want to count, if I want to show you 1 in binary, there we go. There's 1 in binary. So in order when we want to count 2, we cancel this one out and put a 0 when it put a 2 here, 1 here. So 10 is 2 in binary. With these two we can just put zeros in. When we want 3, 2 plus 1 equals 3. See what I mean? We can add 2 zeros here, just to keep the table pretty. Now if we want 4, we cancel these two out and we put 1 here. We put 2 zeros here. So 100 is 4. Let's put a 1 here to complete the table. So if we want 5, we want 4 plus 1 equals 5. We'll put zeros in the other places. So if we want 6, alternatively, we want 4 plus 2 equals 6. I think we're at 6. If we want 7, 4 plus 2 plus 1 equals 7. We'll fill in that 0. Now when we get to 8, we cancel all 3 of those numbers out, so we get 1 here and 0, 0, 0. When we want 9, 8 plus 1 equals 9. When we want 10, 8 plus 2 equals 10. When we want 11, 8 plus 2 plus 1 equals 11. When we want 12, 8 plus 4 equals 12. We want 13, 8 plus 4 plus 1 equals 13. We want 14, 8 plus 4 plus 2 equals 14. We want 15, 1, 1, 1, 1. 8 plus 4 plus 2 plus 1 equals 15. So if we wanted to go on to 16, it would be 1, 0, 0, 0, 0 equals 1, 6. And then we keep going on that table. Now that's a pretty good way of looking at it. But look at it this way: if we want to just draw out all these numbers in binary from 0 to however many numbers, we can do it this way: 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 for the 1 bit, which is all we usually call 0. And for the second one, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. For the third, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. And it keeps doubling and doubling. We got 8 zeros, 8 ones, 8 zeros, 8 ones. And then for the fourth bit, it'd be 16 zeros and then 16 ones. So we're not going to talk about hexadecimal. We're not going to talk about this or that. You can save that for if you're a programmer, or if you're going to school. Like, well, I did a lot of hexadecimal in school. I lived and breathed it for a year. They didn't subject it to us too much in the first year, which was nice. But I hope you get the idea here, because we can use digital circuits, use decimal numbers with digital circuits such as counters, and use them with gates. And you'll see what I mean. Because when we use a 1, if we want to use digital circuits to portray a 1 or a 0, remember, digital circuits work with 5 volts and 0 volts. Analog is many different voltages, but digital is zeros and ones. 5 volts being 1, 0 volts being 0. So So I'll show you something cool. We're going to get back to binary in a second. Right now we're going to talk a little about three friends of mine. We're going to talk about the NOT gate, a triangle with a circle on the end. Oh, that's not very pretty. The AND gate, which has at least two inputs and one output. We're also going to talk about the OR gate, which is pointier, which has at least two inputs and one output. I forgot to mention the NOT gate has only one input and only one output. So we're going to talk about each of these, then we're going to get back to how they relate with binary numbers. First of all, we're going to talk about our truth table. We're going to look at our NOT gate again. Our triangle with circle on the end. Now keep in mind this circle, that little circle. That means to invert or to complement. Now what that means is that whatever's here, whatever digital signal is here, the output's going to do the exact opposite. So what we're going to do is we're going to make up what's called a truth table. We're going to call this input A and we're going to call this output Y. A, Y, 0, 1. 0 or 1. The only two possibilities digitally, which is 5 volts or 0 volts. So if we have 5 volts here, that's 1. If we have 0 volts here, or ground, that's 0. Y is going to be the complete opposite. If we put 0 volts here, we're going to get 5 volts to the output. If we put 5 volts to the input, we're going to get 0 volts to the output. This is the most simple digital gate you can find. Sometimes you'll find an inversion here. Not very often, only in bigger schematics. You don't really have to pay attention to this part if you don't want to. This would mean that the output would equal the input if we put two inversions on there. Then this would be used as what's called a buffer or a current amplifier. So if we have a small signal here, we can make it so we can source more current to the output. That aside, whole different topic. We're going to now do a truth table for our friend the AND gate. Now AND gates and OR gates can have many inputs, depending on what chips you buy. But we're just going to talk about a 2-input right now. We're going to look at a 2-input AND gate. Inputs A and B. And output Y. So we'll make up our truth table. A, B, and Y. So what we're gonna do is we're basically gonna write, since we have two inputs, we've got 2 bits of binary in that sense. So we're gonna write out however many decimal numbers in binary we can. So we're gonna go 0, 1, 0, 1. 0, 0, 1, 1. If we had a third input, C, it'd be 0, 0, 0, 0, 1, 1, 1, 1. But we're not going to do that. We've only got 2 inputs. Oops. Alright, so remember that's 0 in binary, 1, 2, and 3. So there's 4 different input possibilities, no more. So, and the interesting thing about AND is A and B have to equal 1 before Y equals 1. So if A and B equals 0, Y is going to equal 0. If A equals 1 and B equals 0, output's still 0. If B equals 1 and A equals 0, output still equals 0. Only when A and B both equal 0, or all of its inputs equal 1, will the output go to 1. Use these all the time. So take a look at that truth table. We'll get to gates on a breadboard in a little while. But first, let's go to the OR gate. Pointy gate. Let's use a 2-input, OR. Inputs A, B, and outputs Y. Let's make up a truth table. So same thing, 0, 1, 0, 1, 0, 0, 1, 1. Shows us all the possibilities that can possibly occur at the inputs. OR gate works differently than the AND gate. The way the OR gate works is if any input is high at 1, then the output will equal 1. So if both inputs are at 1, then output is 1. If one input is 1, the output is a 1. If the other one is a 1, there's any inputs that are high logic, 5 volts, then the output will equal 5 volts as well. Only when there are no inputs at 5 volts will the output equal 0. So look, you got to keep in mind at all times that 1 equals a 5 volt signal, and 0 equals a 0 volt signal. So now we're going to talk, before we go on to actually showing you how these things work on a breadboard, I'm still going to show you something more. Sometimes you'll come across something that looks like this. It's an AND gate with an inversion on the end, or a complement. This is called a NAND gate. NAND. It's for not AND. It's right on a truth table. So how this works is, what we're going to do is we're going to put A, B, and Y. Now we're going to do this for the AND gate. Remember 0, 1, 0, 1, 0, 0, 1, 1. For a normal AND gate, we'd get outputs of 0 only when the inputs are both at high, we're going to get an output of 1. So the output of a NAND, that line over top of that Y, it basically says that the output is complemented or inverted. So the real output of a NAND gate, is 1, 1, 1, 0. So if you're ever confused, if you're ever looking at a gate and you see an inversion on the end, think of what the truth table would be, what the output would be like based on input conditions without that inversion, and simply invert your output. And that's what you're going to get. So realistically, I don't need to put that in there, but to explain it to you, I know it's a bit confusing. The way they have this set up is while the only time you'd ever get a high output with a normal AND gate when both inputs are high, you'd get a 0, and all the rest of them would be 1. So it's essentially like doing this. Taking an AND gate and connecting it to a NOT gate. You see what I mean? I hope that's clear. It's a little bit off. It's a little bit hard to comprehend maybe, but you'll get it. So let's do the same thing with an OR gate. I have an OR gate's pointier. So now it's going to, with an inverter on the end, it's a NOR gate for not OR. A, B, Y. So remember, I'm using Y here as an example to say what it would be without the inversion, and then Y inverted. So 0, 0, 1, 1, 0, or rather, sorry, my bad. So 0, 0. Normal output would be 0. 0, 1, 1. 0, or 1, 0, 1. 1, 1, 1. I'm going a bit quick here, I know, but you're going to have to bear with me. So if you remember, it says that any input equals 1, any single one of them, or both of them, the output equals 1. But if we put that complement on the end, if we put that inversion on the end, then the output is 1. It's the opposite of what it would normally be. So 0, 0, 0. So if we have a NOR gate, that's what the output's going to be. You can get NOR gates. What's a good example of a NOR gate? You'll probably use NAND gates a heck of a lot more than you'll use OR gates. But again, if you want to look at this from a more practical point of view, then realistically it's just an OR gate, remember, OR gate connected to a NOT gate. So whatever's here gets inverted. That's looking at it in a more practical point of view. So let's show you how we're going to connect some of these up. I'm not going to do all of them, but we're going to connect a couple of them up on a breadboard. Alright guys, so here's the pinout of a 74LS08. I've got it right here on my board. So here's the pinout. We've got 4 2-input AND gates on this chip. Here's pin 1, notated by the little notch on the side. You can always see it. There's always a notch or a little hole on the left side, so to notate where pin 1 is. There are 14 pins on this chip. 7 is the ground pin. You must ground it or else the pin won't work. 14 is what we call VCC. And what VCC is, it is the digital power line. So you have to connect VCC to 5 volts. Okay? So we've got 4 2-input AND gates on here. All we care about is, we're just going to use one of them. There's always 2 inputs and 1 output. Pardon my penmanship again. I'm used to using AutoCAD. I use AutoCAD for just about everything. So what I'm going to do is I'm going to show you how I'm going to hook this up. So this is a 2-input AND gate, remember. I've got my power supply chip, my 78L05, hooked up. I hope you were watching this in order, guys, because I showed you how to hook up a 78L05 5-volt regulator. Remember, if you hook up more than 5 volts to this chip, you can very easily damage it. So what we're going to do is we're going to hook up, first of all, we're not going to power up our battery, but first we're going to take our, we're going to ground our chip. So we want to take a black wire. You don't have to use a black wire, but it's just a nice thing to do. It's nice to know what's connected to where. And pin 7 on here, of course, is right here. Remember, we're looking at it. Pin 1, pin 7, far right. Top right is pin 8, and top left is pin 14. So we're going to bring it up to our ground line from the top. We're going to ground it. That's step 1. Step 2 is to connect power to it. Now keep in mind we are not plugging in our battery just yet. Normally I'd be using much shorter wires, but I'm just using what's available. So that will go to our top rail, our power rail. There we go. It's now officially connected to our 5-volt line. So pin 1 is an input, pin 2 is an input, and pin 3 is an output. So here's what we'll do. Actually, you know what? Pin 13 is an input, pin 14 is an output, and pin 12 is an output. So let's just connect one of those inputs to ground. We'll connect the other input just to an open line. We're not going to connect to anything right now. We're going to take what's called an LED, a light emitting diode, and I'll tell you more about light emitting diodes a little bit later, not in this lab, but in another one. Light emitting diodes can only be placed in one way, or else it won't work. It has to be placed with the anode connected to the power supply, positive power supply, and the cathode to ground. So we're going to put the cathode, and as I said, you won't have to understand this now because we'll talk about it later, in the output line, and the anode in the output line, and the cathode, the negative is the cathode, into the ground line. So whenever the input selections are correct, our output line will go high. And by high, it'll show you the indicator LED will go off. So let's experiment with this. Remember how an AND gate works. An AND gate works, if both of its inputs are high, then the output will go high. Otherwise, it'll stay low. So let's plug it in. We are now officially plugged in. Remember, one of its inputs right now are grounded. So I can take this pin right here and connect it manually to the 5-volt line. Oops. My wire fell off. Okay. I'm going to use another one. That's never fun when that happens. Okay, so I can connect it to either the 5-volt line or the ground line, and nothing will happen because the other input is connected to ground. So let's connect this one to our 5-volt line. So right now we've got an input at 5 volts, which is a 1, and an input connected to ground. As soon as we connect that other input to 5 volts, the output goes high. Now notice something. If I take both of the inputs and leave them alone, don't plug them into anything, the output stays high. I'll tell you why that is. Because with TTL, with digital circuits, normally, not in all cases, but most of the time, if an input is not connected to either 5 volts or 0 volts, by 0 volts I mean a very low signal or the ground line, then it will automatically assume a logic of 1. So if I ground either one of these, then the output goes off. If I take it off, you don't want to leave these floating. That's what's considered floating. So that's the AND gate. If we ground any of the inputs, the output is off. Commonly, we'd have signals coming in, high or low signals, to determine the output. But for now, let's move on to another chip, shall we? All right, guys. So this is an OR gate. Ow! The exact same pinout as the AND gate we just used. This is a 74LS32, but we're using OR gates. So I haven't powered it up yet. What I'm going to do is I'm going to ground both the input signals. Before I power it up, I'm going to put it to the negative line. So both inputs are going to be grounded. Okay, so now I'm going to plug it in. LED is off. As soon as I take any of those off the ground line and leave it floating, it's automatically assuming a power level of 1, or a logic level of 1 rather. High or low logic. 5 volts, high logic. 0 volts, 0 logic. So now one input is grounded, one input is not grounded, one input is held at high. So I can do whatever I want with that second one. I can ground it, I can put it 5 volts, it doesn't matter, because one of the inputs is already at high logic. So it doesn't matter what I do with the second one. So digital gates are very, very simple. You got to look at the data sheets, you got to find the pinouts, you got to make sure that you ground everything properly, and you're limiting the power supply to 5 volts. And yeah, just going to be really careful. I'll show you a couple more. I'll show you the NOT gate and I'll show you the NAND gate, and then that's going to be all for this lesson. Hold on for 1 second. Okay guys, this is a NAND gate. So remember, the output of an AND gate will only go high when both of its inputs are held high. So oppositely, if we turn on the power and put both of the inputs high, then the output will go low. Otherwise, no matter what, the output will stay high. Now remember, if you need to go back, or simply just Google NAND gate or AND gate, and you'll understand, you'll get a truth table of it. But try to remember it, because it's not hard to memorize. So let's power it up. Let's start both of the inputs at high logic. So it should stay off when we power it on. Okay. So the circuit is, the chip is properly powered, properly grounded. Both inputs are at high. So since it's an inversion of the output of an AND gate, the output is low. We bring any of the inputs to ground, the output goes on. Any of them. Either or both. It doesn't matter. If we bring either one of the inputs to ground, the output goes on. So you can use these in all sorts of crazy stuff, and you won't know what to use them in right now, but you'll see how I use them in different things. They're really neat. They're helpful with resetting certain units. They're really a lot of fun to play with. So hold on, I'm going to show you the NOT gate, and then that'll be it for this lesson. You'll understand more about working with binary, working with gates, and working with other digital circuits as we go on, and you'll be able to build some crazy stuff. Hold on for 1 second, I'll show you the NOT gate. Alright guys, this is the 74LS04 NOT gate. We're going to power it on. we've got, it's one input. Remember, NOT gates only have one input and one output. The output is an opposite of what the input is. So right now we've got the input at ground, at negative. So we expect that as soon as we turn it on, there you go. So as soon as I unplug this, it's gonna, by default, the input is going to be it's going to assume 1 by default, which is going to go to low. So right now the input is at 5 volts, the output is at 0 volts. It won't read 0 volts, but it'll be below half a volt. Usually inputs of digital devices, especially TTL, read between something like 0.8 volts and below is considered low, and above half VCC, which is 5 volts, above 2.5, 2.8 volts is considered high. So I hope this lesson has proved interesting. You'll see more about how I'm able to use all this stuff later on. I've got tons of video ideas. I'm going to be making them for the next little while. Like, I'm going to be showing you how to build some pretty cool stuff. All those are different circuits. So thanks a bunch for watching. I hope you keep watching my videos. I hope you keep spending the dollar. I hope it's worth it for you guys. Thanks a lot, guys.